All right, to summarize, here are the three possible scenarios for your auxiliary equation. The first case, very common, is to have distinct roots. Distinct roots. And we have seen this with the equation y double prime minus 5y prime plus 6y equals 0, which gave the auxiliary equation r squared minus 5r plus 6 equals 0, which basically gave r equals 2 or 3. In which case we had exponential solutions. So y was a e to the 2t plus b e to the 3t. That was one scenario. The second scenario was repeated roots. For instance, with the equation y double prime minus 2y prime plus y equals 0, in which case the auxiliary equation is r squared minus 2r plus 1 equals 0. And that gave r equals 1, which is repeated. And the only thing you have to remember here is to add this extra t. So the solution is a e to the t plus b t e to the t. E to the t. And this extra t, if you remember, came from integrating a constant in the factoring method. And last but not least, we have complex roots. Like in the equation y double prime minus 4y prime plus 13y equals 0, which gives, whose auxiliary equation is r squared minus 4r plus 13 equals 0. And then by completing the square, you get r equals 2 plus minus 3i. And that's when the cosines and sines appear. So in this case, y is a e to the 2t, so e to the real part t, cosine of imaginary part, 3t plus b e to the 2t, sine of 3t. And the good news is, so those are really all the three cases there are, at least for constant coefficient second order equations. But also what's nice about this, for higher equations, it's pretty much the same. So for instance, let's try to solve the ODE, whose auxiliary equation is r times r minus 1 times r minus 2 cubed times r squared minus 4r plus 13 squared equals 0. You do not need to find that ODE. I already give you the auxiliary equation. So in this case, we just have to find the roots and repeat whatever we've done in the above. So the roots are r equals 0, r equals 1, r equals 2, but it's not repeated twice, but 3 times because of that cube. Times, and r equals 2 plus minus 3i, and here it's repeated twice. Twice. So in this case, what's the solution? Well, y is, so a e to the 0t, which is just a, so constant, plus b e to the t, that comes from the root 1, plus. So for this r equals 2, we get, well, since the root is 2, ce to the 2t. Since it's repeated, dt e to the 2t. But that's if it's repeated twice. Since it's repeated 3 times, you have a et squared, e to the 2. So however many times it's repeated, you add extra terms here. And then for this 2 plus minus 3i, as before, we get f e to the 2t cosine 3t plus g e to the 2t sine of 3t. But because it's repeated twice, you have to redo this with an extra t. So ht e to the 2t cosine of 3t plus it e to the 2t sine of 3t. And that is your solution. So once again, the moral is, as long as you can factor out the auxiliary equation, you can actually solve the ODE. So for our purposes, we can solve all constant coefficient homogeneous ODEs. And one of the next topics will be inhomogeneous ODEs, where the right-hand side is not 0.